So today we will be discussing about basics of vibrations. So definitions, so basic definitions in vibrations, and also we'll be discussing types of vibration. So basically, first we'll understand uh, what are the elements involved in a basic vibrating system. So the basic elements. So the basic elements are a spring, a mass, and a damper. So basically, this is a spring, and this is a damper, and this is a mass. So mass is denoted by M. So stiffness is denoted by K, and the damping is denoted by small c. So basically, different elements are there. So these are the three elements. So the damping is basically dissipation of energy. So that is resistance to motion. Resistance to motion. For example, so if you are walking on a path or a floor, so it is very easy to move from point A to point B, because the air resistance is lesser. So similar example, if you compare with a person moving in a swimming pool, if he is walking in a swimming pool, so it is similar to the resistance to motion. So there, whatever the motion is having resistance, so that is due to the water. So similar way, so the damper is giving resistance to the motion. So similarly, we have spring. So basically, it is to store the potential energy, and we have mass. So that is for storing kinetic energy. So basically, if you write the equation for kinetic energy of the mass, so it will be half m x dot square. So whatever displacement we have here, so that will be x. And if you write the potential energy, so that will be half k into x square. So basically, x is displacement. So x is displacement, x dot is velocity. So how we are deriving these equations? So for example, uh, the mass is having a force, so that is equal to F is equal to m into g. So this is a basic force equation, so everyone knows that. uh, so next, if you want to write a force for a spring, so I'll write it as Fs, so that is equal to k into x. So if you want to derive this forcing term, so you have to consider a spring. If you consider a spring, so which is having a stiffness k, so same spring, if I put a load, it will expand. So I'll put a load of mass m, so it will expand. So it will move from this point to this point. So here it is having a displacement. It is displacing from this point to a new point. So it is having a displacement x. So basically, here you can write the force is directly proportional to the displacement. So if you plot a curve, you will get F versus the force versus the displacement. So it will be a linear curve. So the under the slope, if you take, so that is force is directly proportional to x. So here you can write F is equal to k into x. Force is equal to k into x. So this is how we can derive the force equation for a spring. So similarly, if you take a damper, if you take a damper, So here what we can write, so the damper coefficient is C. So if you write F is equal to K into X for a spring. So similarly, for a damper, we are writing F is equal to C into X dot. So basically, here the force is directly proportional to the velocity. So these are some basic forcing functions for spring and a damper. So if you want to write a free body diagram for the given spring mass system, so basically you can call this as spring mass damper, SMD. Basically you can call it as a spring mass damper system. So if you want to draw a free body diagram, so basically you can draw in this form. So first write down the mass M. So if we are pulling this in downward direction, so the inertia force will act in opposite direction. So that is M into X double dot. So similarly, the inertia force is acting in opposite direction. Here the spring force is also acting in opposite direction. So that is K into X. So already we have mentioned it here. So similarly, we have a damping force, so which is over here. So here we can write, so the force is Cx dot. So there is no any other force involved. So this is the FPD, free body diagram of a spring mass damper system. So if you want to write the equation, so it will be, you have to take the summation of forces in y direction is equal to 0. So according to D'Alembert's principle, so we can write mx double dot plus cx dot plus kx is equal to 0. So basically this is called as equation of motion. So this we can call it as EOM. So this is equation of motion. So whatever things we have studied till now, so we have derived equation of motion. So before that we have written a free body diagram. So we have understood what are the basic elements involved in a spring mass damper system. So now we can define what is vibration. So vibration, a motion which repeats itself after equal interval of time. So uh, if it repeats after equal interval of time, so that is called as simple harmonic motion. So if there is a unequal time, so that is called as aperiodic motion. If it repeats, the motion repeats after certain interval of time, so it is called as vibration. So basically, three definitions are there. One is SHM, so the motion which repeats itself after equal interval of time, so unequal interval of time. The motion which is repeating after a certain interval of time, so that is called as vibration. So I'll erase all the slides. So I'll draw a SHM motion. Here you can see, so whatever amplitude is there, so that is equal. So this the maximum. So this is amplitude A. So the maximum displacement of the vibrating body from the mean position. So that is amplitude. So next is time period. So this is time period T. So time period, it is time taken to complete one cycle. So whatever one cycle is there, so the time required to complete one cycle is called as time period. Next is frequency. So number of cycles per unit time. So in, for example, if this is a 1 unit time, so next this will be 2. So number of number of cycles per unit time, so that is called as a frequency. So if you want to define a natural frequency of the system, so that is denoted by Fn. When there is no external force acting on a body, so basically it's a kind of a free vibration. uh, the frequency of free vibration is called as natural frequency, so that is denoted by Fn. So, and also we can write the axis. So this is time axis T, and this is the displacement X. So after this, we'll see so different types of motions for different types of systems. So first we'll consider a spring mass system, a simple spring mass system, which is having a spring is having stiffness K and mass is displacement X. So if you draw a response for this, so this is time axis and this is displacement axis. So basically, if I pull it down or push it, so basically, so that is going to give initial displacement. So that is x naught for a free vibration. So it will start from this point x naught and it will start to oscillate in a SHM motion. So basically, so this is a SHM motion. So SHM motion already we have defined. So the motion which repeats itself after equal interval of time. So that is called as SHM motion, or it is called as periodic motion. So, so basically, so this is the response for the given system. So for example, so this will consider it as 1. So if you write equation, so it will be mx double dot plus kx is equal to 0. So this is first system. So similarly, so if I take a system, a spring mass damper system, so I'll take a spring, a damper, and a mass. So basically, so this is C. So this is the mean position. So again, displacement X. So the time axis. So again, we are starting from point x naught. So that is initial displacement. So if we start in this case, so here we got a simple harmonic motion with the same amplitude throughout. So in this case, what you'll be getting, so here we have a damper. So here the system show a decay kind of response. So after some time, so the system will come to a decay. So it will, so gradually the system will come to a zero position. So for this, if you write a equation of motion, so again we will be getting mx double dot plus cx dot plus kx is equal to 0. So the first case and the second case are for free vibration. So basically here we are not considering any kind of force in the system. So now we'll consider a few systems, so similar systems with forcing function. So for example, this is a third system. So same spring mass system with the forcing function. If you take F force, so this is the main position. So again here you can see such a motion, so with the same amplitude. So this is initial displacement x naught. So here you can write equation of motion as mx double dot plus kx is equal to f. Here you can consider it as f naught sine omega t, and also you can write f naught sine omega t. So this will be the response when you consider a forcing function. Similarly, the fourth case. So here we will consider a spring, a damper, and a mass. C. Here we will consider a force F naught sine omega t. So again we will draw main position. So this is displacement x, and this is time t. So again we are starting from here. So again, so the response will be simple harmonic motion. Simple harmonic motion. For example, if this omega, the omega value, so if we vary for a different set of parameters, so if you draw the plot, so basically you'll be getting, if I draw amplitude versus frequency plot, so you'll be getting a bell-shaped curve. So at different values of frequency we are plotting, so the frequency is omega, so and the system will be having a natural frequency, so that is omega n. So this omega n is natural frequency. So we'll get a bell-shaped curve for different values of omega n. So omega 1, omega 2, so till omega n. So this is excitation frequency. Excitation frequency. So at this point, so that at this point the amplitude of the system is maximum. As you increase the frequency from 0 to a limit, so at some point, so we will get a maximum amplitude. So that point is called as a resonance. So that is when the natural frequency of the system omega n matches with the excitation frequency omega. So at that point we can see a resonance. So the best example is tuning fork experiment. So in that tuning fork experiment, so you can see when the natural frequency of the system is excited, so you can hear a sound. So basically, we'll continue different types of vibrations in an upcoming video. So different types of vibrations are free vibration, forced vibration. So already we have discussed what is a free vibration, what is a forced vibration, what's a forced vibration. So also we have deterministic vibration, random vibration, longitudinal vibration, transverse vibration, torsional vibration, and transient vibration. So basically, in the upcoming video, so we'll see different types of vibration.